dear students. So in the today's class, we are discussing some of the note which I explained in the last previous class about the empirical formula for different spectral series. So you should remember these three important notes, and also I'm going to explain you the drawback of the Rutherford atom model. Okay. So as I explained you in yesterday's class about the empirical formula, how to find out the wavelength of each spectral line, right, of each spectral series. There I explained you about the Balmer series, Bastion series, bracket series, Clifford series, okay, Lyman series. Okay. So you should remember the first note. You should remember that in any given series, first spectral line has a maximum wavelength. Okay, and I think you might have remembered that diagram which I explained in the last class. So first spectral line H alpha, H beta, H gamma, H delta. So we can observe here that each of the spectral line, if we go further, we can observe they are lying very close to each other. So in Balmer series, when we are observing the four spectral lines here, first one H alpha, that means red, second blue, green, violet, like this, and so on. Right. So this first note, what it says that in any given series, say for example this is a given series, the first spectral line has always maximum wavelength. So what I have written here in the first spectral line of Balmer series, 656.3 nanometer, okay, which has a maximum wavelength. And the last spectral line among the four spectral lines, this one is the first, second, third and fourth, which is the last spectral line, has a shortest wavelength. Not only for this Balmer series, even for Lyman series, in Paschen series, in bracket series, in Clifford series, where we are observing the spectral series, there always you should remember that the first spectral line has always a maximum wavelength, and the last spectral line has always a shortest wavelength. Has always shortest wavelength. So this point we should remember. So the second note, what it says that each series terminates when n2 is equal to infinite, and wavelength corresponding to this transition is called as series limit, or you can say it is the shortest wavelength. Say for example, we are considering the Balmer series here. Example I am saying you. This is the Balmer series. There we are having the four spectral lines. Not only we are having the four spectral lines, we are having more than four spectral lines. So the last series, okay, which comes in further, when we move further, we are having the last series which terminate, where the series terminates, मतलब जहाँ पे ये series terminate होता है, उस लास्ट सीरीज का जो n2 का वैल्यू होता है वो क्या होता है, वो इनफाइनाइट होता है. It is having an infinite value. So here for example, I have explained you the empirical formula 1 by lambda is equal to r into 1 by n1 square minus 1 by n2 square. 1 by n1 square minus 1 by n2 square. Here for Balmer series we are having n1 is equal to 2 and n2 is equal to 3, 4, 5, 6 like that. Okay. N2 is equal to 3, 4, 5, 6. So we are having many spectral lines here. So the last line which terminates the series, because each series is going to be terminated. So whichever is the last line, that value is always there. I can take this as n2 is equal to infinite. That is the last one, infinite. N2 is equal to infinite. So that is what we say, that each series terminates when n2 is equal to infinite at wavelength corresponding to this transition is called as series limit, or you can say it has the shortest wavelength. See, this one is the least wavelength here. If we go further of this where it is going to be terminated, in the decreasing order we are having, which I explained in the last class also. Okay, so which has the shortest wavelength. And to find out the frequency of the each spectral line, we are using this formula. Nu is equal to R into C 1 by n1 square minus 1 by n2 square. So as we are having it here, we can write this as 1 by lambda is equal to nu by C. So this 1 by lambda can be written as nu by C equal to R 1 by n1 square minus 1 by n2 square. So this can be written as nu is equal to R into C, that is 1 by n1 square minus 1 by n2 square. So this finds the frequency of the each spectral line. We can find out the wavelength, and also frequency of the each spectral line. So this is all about the important note you should remember, which will be very helpful while solving the numericals. Next, our topic is the drawback of Rutherford atom model. What is the drawback of the Rutherford atom model, or you can say disadvantages of the Rutherford atom model, or you can say failures of the Rutherford atom model, where the Rutherford failed to explain some of the points regarding the atom model which he explained. So the first drawback is that Rutherford's atom model fails to account for stability of the atom. Rutherford failed to explain the stability of the atom. According to the Rutherford atom model, what he says that in an atom we are having a nucleus, and around the nucleus the electron is going to be revolved continuously. The electron is going to be revolved. So, example I will tell you. Suppose myself continuously I am taking the class, 1 hour, 2 hours, 3 hours I am taking the class. My energy is going to be exhausted. For first hour I am having the full of energy. In the second hour my energy is going to be decreased. In third hour, when I am taking the third hour class, again my energy is going on decreasing. In the same way, the electron which is revolving around the nucleus in its orbit, okay, this electron continuously it is going to be emit its energy in the form of radiation. So it is going to emit its electromagnetic waves. So simultaneously, what happens when it radiates its energy while revolving around the nucleus? This electron may fall towards the nucleus, because slowly it is going to decrease its energy here. So that is what he says, that no such atom is a stable here. This point we did not explained here. So that is what the drawback of the Rutherford atom model. So he could not able to explain about the stability of the atom. So Rutherford atom model fails to account for stability of the atom. So from this we can know that no such atom is stable here. So where the electrons which are continuously revolving around the nucleus, they emit their energy in the form of electromagnetic waves, in the form of radiations. So that is how this electron may fall towards the nucleus. Slowly what happens? The radius goes on, decreases. Here it comes here. Next it comes here. Next it may fall into the nucleus. So that is what he failed to explain the stability of the atom. So from this we can say that no such atom is a stable. Right? So this is the one first drawback of the Rutherford atom model. It fails to account for the stability of the atom. Second, Rutherford's atom model fails to account for spectrum radiation emitted by the atoms. So as I told you that when an electron which is revolving around the nucleus, it emits the radiations. Right? So there its angular velocity, the electron which is revolving, right? The electron which is revolving around the nucleus because of due to the centripetal force. So there the angular velocity and the frequency of the electron the emitted radiations goes on decreases. Angular velocities and the frequency goes on decreases. So that is what he failed to account for the spectrum radiation emitted by the atoms. Okay. So while revolving, this electron which is emitting the radiations, they are observed in the form of there is spectrum of radiation emitted by the atoms. So that he was not able to explain. Here angular velocities and the frequency goes on decreases. Right? So these are the points we should remember here. So next we move towards the next Bohr's atomic model. So our next topic is Bohr's atomic model. So what the Bohr's atomic model, what he postulates the 3 points here. The first postulate is that an electron in an atom cannot revolve in all possible orbits but can revolve in a certain permitted orbits called as stationary orbits. So what he says that an electron in an atom, say this is an atom and where it is a nucleus and the electron is revolving around the nucleus here. An electron in an atom cannot revolve in all possible orbits, but it can revolve in a certain permitted orbits. Those orbits are called as stationary orbit, or also you can call it as a non-radiating orbit. Stationary orbit is an orbit where the electron is not going to be radiate its energy while revolving. Such orbit is called as stationary orbit, and it is called as or also it is called as a non-radiating orbit here, where the electron is going to remain its stable orbit here. Such orbit is called as stationary orbit. So once again explain here, an electron in an atom cannot revolve in all possible orbits, but it can revolve in a certain permitted orbits. Such orbits are called as, that is, stationary orbits, or it is also called as non-radiating orbit. This topic is very very important, dear students. In exam point of view, they might ask in the exam very very important postulates, that is Bohr's atomic. Sometimes they might ask explain the Bohr's postulates, Bohr's atomic model or Bohr's postulates. Second postulate, what it says, that the electron revolves around the nucleus only in those orbits for which the angular momentum is an integral multiple of h by 2 pi, where here we are having L is equal to what? Angular momentum. L is equal to n raised divided by 2 pi. N is equal to 1, 2, 3 dash dash. Okay, so whichever the electron which is revolving around the nucleus in those orbits, its angular momentum is always equal to an integral multiple of h by 2. Here n is equal to integral. N is equal to, it is an integral multiple. That is where n is equal to, where n is equal to 1, 2, 3. 1, 2, 3 dash dash. Okay, so this is what the second postulate. Third postulate, what it says, that atom radiates energy only when electron jumps from a stationary orbit of higher to a stationary orbit of lower. Right? So while jumping the electron from higher orbit to, say for example, this is the higher orbit and this is the lower orbit. Electron is jumping from higher orbit to lower orbit. Okay. While jumping this electron from higher orbit to lower orbit, it radiates its energy. That energy is radiated in the form of photon. So as that photon which is emitted, its energy is equal to, it is the difference between the two energy levels. So once I am explaining here, say for example, this is our atom. Here we are having this. Right? Here the electron is in higher orbit. So the electron, the atom, the complete atom radiates its energy only when electron jumps from higher orbit to lower orbit. Higher stationary orbit to the lower stationary orbit. So while jumping the electron from higher orbit to lower orbit, during this it emits the radiations. Those radiations are in the form of, that is, photons, and those photon is having that, the photon which is emitted while jumping this electron from higher orbit to lower orbit, that photon energy, that is photon energy, is always equal to the difference between the energy levels. That is this is E1 and this is E2. Difference between the two energy levels, that is initial and final. Okay, so that is what h nu is equal to. E means what? Energy. Energy means which can be written as h nu, that is E2 minus E1, or also you can write nu is equal to E2 minus E1 divided by h. Okay, so we should remember this one. Atom radiates energy. The atom radiates its energy only when electron jumps from stationary orbit to the stationary orbit of higher orbit to a stationary orbit of a lower energy. So while during this transition, electron is going to be emit its radiation, right? So that emitted radiation is in the form of photon. So the photon which is emitted during the transition, its energy is equal to the difference between the initial energy and the final energy states. There is h nu is equal to E2 minus E1. There is nu is equal to E2 minus E1 divided by h. Where h is the Planck's constant. Here h is the Planck's constant. H is the Planck's constant. Okay. So this is all about the today's class. That is Bohr's atomic model which we discussed. So which is very important for the exam point of view. very important topic. So they would ask in the exam. Okay, so practice this post-academic model for 5 times in your home. Okay, because in the exam point of view it is very important. Okay, so today we'll stop here. In the next class we'll continue with the new topic. Thank you.